Let me introduce the speaker. Dr. Kiel Howe received his PhD at Stanford University. His advisor was Dr. Peter W. Graham. His PhD study was focused on testing of supersymmetry at the LHC. Now he is a postdoctor in the Fermi Lab, National Accelerator Laboratory Theory Group. The title of his talk is Naturalness and Signatures of 5D Susy at TeV scale. Let's welcome the speaker.
Thanks for the introduction and for having me here. It's great to still be here again today. So today I'm going to talk about some supersymmetric model building, motivated by this idea of naturalness. Yesterday I talked about kind of future colliders, but today I'm just going to focus on what we've learned about naturalness at the run of the LHC so far, and just a little bit about what we might hope to find out at the 14 TeV run of the LHC. So let me just start off with a little bit of introductory material, and I'm going to repeat. I'm sorry if you saw my talk yesterday. I'm just going to use the same slide and introduce supersymmetry just for if anyone wants a quick introduction to this before I dive into why this is a good way for understanding naturalness at LHC. Okay, so supersymmetry is an extension of the symmetries of the standard model. It's kind of the maximal non-gauge extension of the symmetry of the standard model. So the standard model has the gauge symmetries and Lorentz symmetries that we've discovered. And there's one extra space-time symmetry you can add to the model called supersymmetry that takes all of the standard model particles and pairs them with particles, new particles that have different spins. So the standard model quarks and leptons get paired with new spin-0 scalar particles called squarks and sleptons. And all these spin-1 particles, the gauge bosons, electroweak gauge bosons, and SU3 colored gauge bosons, get paired with spin-1 half particles, the neutralinos and charginos, and the gluino, which is charged under color. So there's a number of motivations, some simple and some complicated, for thinking about this kind of model as an extension to the standard model. And this is kind of a framework. The minimal supersymmetric standard model is a framework for extensions beyond the standard model that has generated a lot of the searches and motivated a lot of the searches at the LHC. So it's a good context to understand the LHC results within. Just some of the motivations for studying the standard model are coming from UV completions of gravity. So the only simple UV completions of gravity that we know of involve supersymmetry, gauge coupling unification, the idea of naturalness, that the weak scale is not an accident, and many models of WIMP dark matter fit nicely into supersymmetry. So there are a number of reasons to think about this kind of theory, and there are quite a few different ways to look for this theory at colliders, but I just want to kind of describe the general thing that you might look for at a proton collider to look for supersymmetry. Because I have many particles in the MSSM, there are many different ways I could look. There are many different things I could produce at the LHC, many different ways they could decay, and many final states I could look for. But kind of the most generic thing that you expect to see is that because there are new colored particles and the LHC is a proton-proton collider, it interacts most through the strong force, with the largest cross-section through the strong force. So you'll have much larger production cross-sections for any colored particles in MSSM than any non-colored particles. So the first things that you would expect to see in general are the colored particles of the MSSM. So for example, you might produce a pair of stop squarks. So the superpartner, the scalar superpartner of the top quark at the LHC, and the collision by combining two gluons together. So the gluon fusion process that produces a pair of top squarks. Now in the simplest versions of the supersymmetric models, I have all of the superpartners, so all of the new parts I've added, carry an extra conserved quantum number called R parity, which just says that I never produce a single superpartner on its own. I always produce a pair of superpartners or an even number of superpartners. And likewise, when these superpartners decay, so I produce them, but in general, my colored partners will live only for a short time, and then decay back to standard model states, and to whatever the lightest supersymmetric particle was. Now, if this R parity is exact, then whatever the lightest new particle I added to my model is going to be stable on cosmological timescales, and there's very strong limits on whether this particle can be charged or not, so this particle has to be neutral. And that means that all of my decays of the colored particles I produce will end in some final state with a bunch of standard model particles. So in this example, the stop squirt decays to a top and this lightest supersymmetric particle, which might have been one of the gauginos, for instance. And this gaugino has to be neutral. This LSB has to be neutral, so that at the LHC, it just passes through my detectors, much like a neutrino would just escape from the LHC without being seen because it has such a low interaction cross-section with the materials of my detector. Okay, so what you look for is events where you see a lot of energy in standard model particles, in leptons and in jets, but also kind of the generic signature you might expect from supersymmetric models is to also have a bunch of invisible energy, which looks like an imbalance in the energy conservation. So just like how the neutrino was discovered in radioactive decays from an imbalance in the energy conservation, you add up all the energy that comes out and you see that it looks like something was carrying away energy that you didn't see. So this is just kind of the general way you look for these particles. You can go beyond this simple picture and generate a variety of different signatures in these models. But this is kind of the most generic thing people look for. Okay, so we've been running the LHC for several years now, and the ATeV run has been completed, and most of the analyses at the ATeV run have been completed. And the result of all these searches for superpartners can be summed up in, we didn't find any superpartners. So if you have this kind of generic scenario where you're producing colored particles dominantly and they decay to final states with invisible energy, then the limits on these particles are around, for the first and second generation squirts, and for the galeno, around 1.5 to 2 TeV for their masses. And if their masses are greater than that, then it just means we wouldn't have produced enough of them to have been able to see it in the searches that we did over the background. The limits are a little bit less tight on the third generation squirts. That's because these states have a slightly smaller cross-section than the first and second generation squirts. And because their decay modes are a little bit more challenging to see because they decay through third generation particles. So these limits are around 600 or 700 GeV. And then there are also limits, one interesting limit is on the superpartner of the Higgs boson, which is called the Higgsino. And this limit is a little bit more model dependent, but it's around 300 GeV. Okay, so this is kind of the current status of the direct searches for superpartners at LHC. We also learned something else very interesting at LHC, which is we discovered a Higgs boson that has properties that are very standard model-like. And what I mean by standard model-like is its branching ratio to different states seems to match the predictions of the standard model within about 10%. And what that means in the context of supersymmetry is that there's probably some type of decoupling limit where supersymmetry predicts that the Higgs sector has more than one doublet, so you don't just have the normal standard model Higgs doublet, but also an additional Higgs doublet, at least one, possibly more. And what this result is telling us is that there must be some decoupling limit where the extra Higgs states are much heavier than the Higgs we've discovered, so that you can reproduce the results that the Higgs looks like a standard model Higgs. Okay, so should I be worried about finding supersymmetry at the LHC because of these results? And people are worried, and people have been worried, and kind of the important thing for interpreting these results is that in the simplest versions of supersymmetric models, if you combine that with the idea of naturalness, which is, the idea of naturalness is really the idea that aren't any connections between different energy scales other than quantum field theory, and we're not super unlucky. So this combination of ideas tells you that you would expect the masses of the superpartners in these simplest models to be about the same as the Higgs mass. right? So they should have been around a couple hundred GeV, and then you would have seen these particles produced at LHC. So this is led to a little bit of a naturalness panic from the LHC results. Okay, and this has been a good thing in the modeling community. So this has led to a lot of interesting work in the past few years to try and understand what this might mean for supersymmetric models. So one direction you could take this is kind of an existential crisis. Is naturalness really a good principle to, this idea that there is only the connections between energy scales that we understand from quantum field theory? Is this really a good prediction of new physics at the weak scale or not? And there's been lots of interesting work on this in the context of the landscape, of dynamical mechanisms, in cosmology, in early universe cosmology for setting the weak scale with a different set of dynamics than supersymmetry, of understanding what kinds of theories might not have the same kinds of connections between energy scales. So this has led to a lot of interesting things, and I think you can kind of summarize the work in this direction in the idea that naturalness is a principle that predicts that you should absolutely find new particles at the weak scale associated with Higgs. In my opinion, I think, and in a lot of people's opinion, it's not a firm prediction that you should find these things. However, it is still a very interesting question to ask: are there new states that make the standard model natural near the weak scale? So I think it's really a question, not a problem, and we learned something interesting either way, whether we discover these new particles or not, about the nature of the weak scale and its relation to any other scales in beyond standard model physics. Okay, and then the other interesting thing, direction that this has led is on the idea of minimality. So most of the general arguments we make that you should find all of the superpartners that we should have seen them by now have to do with assuming that we have the most minimal version of the supersymmetric standard model. And so it's an interesting question to ask: are there models that are perhaps more complicated, that don't have the simplest minimal extension of the standard model, but that are still natural, so don't have this tuning that the minimal realizations do too? And that's the direction I'm going to look at in more detail in this talk. Okay, another very interesting direction has been in how do you hide supersymmetry. So if you produce colored superpartners and they decay to standard model particles and missing energy, that is a very clear signature to see, because missing energy, there aren't very many processes in the standard model that give you invisible particles. So there are background processes that give you final states of neutrinos, but these generally have very low cross sections. So this is a very good way, and this is where these strong limits of 1.5, 2 TeV on colored particles come from. But there are lots of ways to arrange a supersymmetric spectrum or a supersymmetric model that doesn't have that signature. And there's been a lot of interesting work both in developing on the theory side these kinds of models, and developing on the experimental side new searches to try to cover these kinds of models. So some examples: if this parity that guarantees that you always decay to a stable supersymmetric particle called R parity is violated by a little bit, then you can have final states that are all standard model particles and don't have any missing energy. And this can affect the limits quite a bit. And so there are a variety of things along this line of changing the signatures of supersymmetry that have been studied. And you can also kind of sum up the results of this. And I think the interesting conclusion is that the limit on the lightest colored superpartner can be pretty significantly reduced if you play around with the spectrum or the decays of the model. So, for example, if the stop, instead of decaying to a top and the lightest supersymmetric particle, which is invisible, just decays to two standard model particles, then you can reduce the limits on this state by about 50%, so to around 200 or 300 GeV, and this kind of within the naturalness region. However, if you have any colored particles within a factor of 2 or 3 of the stop that you're producing, then you'll have cascade decays where you produce the stop, which does this decay, and then also produce some other high energy particles. And it turns out that although it's a different search, there are also very powerful searches for this kind of state. So if you have these extra decays from heavier colored supersymmetric particles, then there's not much you can do to get around these limits, and the limits kind of stay around 1.5 TeV. So this has been a fairly interesting development, a good interaction between the theory community and the experimental community in closing this gap. Okay, and this tells us something interesting because in many of the models, you're not really just worried about, for naturalness, you're not worried about just the lightest particle, but you're really worried about the entire spectrum of particles, and I'll quantify that in a second. Okay, so one of the ways you can think about the limits and their interaction with naturalness is that I gave you this general formula that the mass of the superpartners should be, all of them roughly comparable to the mass of the Higgs boson. So this is what happens in the simplest versions of model where there are very simple connections between the breaking of supersymmetry and how that's communicated to the standard model. But in more complicated models, you can get different spectra, and the really concrete connection between energy scales is between the mass of the top quark, or the mass of the superpartner of the top quark, the stop, and the mass of the Higgs boson. So those are the two numbers that you expect not to find a hierarchy in, or to find a hierarchy of a factor of a few quarks. So this is, you don't expect to find a big hierarchy between the stop mass and the electroweak scale. And then the other kind of concrete general thing is that in almost all models, except for a few special ones I'll discuss, you expect that the gluino and the stop will have masses very near each other. So the gluino, the colored partner, spin 1/2 partner of the gluon, should not be much heavier than the partner of the top quark. Okay. So the combination of all these things gives you a picture where this limit and the fact that there's a naturalness problem in the standard model seems pretty robust. Okay. Good. So the other thing that we should worry about then is that in supersymmetry, because all of the interactions of the superpartners are related to the interactions that we've already measured of the standard model particles, there's actually a precise constriction of what the allowed masses for the Higgs boson are. And 125 GeV Higgs boson is a little bit heavier than is easy to accommodate in the minimal supersymmetric standard model. So this is another reason that you might expect to find more structure than just the minimal model, the minimal supersymmetric model, is that there are many simple ways to add a little bit more structure to the MSSM and get a 125 GeV Higgs boson mass. Okay, so yes, kind of the summary is that there is kind of this robust problem of naturalness and the LHC results, unless I'm willing to look at extensions beyond the MSSM that involve new states beyond just MSSM states at a low scale, so at the TeV scale. So that's the direction we're going to go. Okay, so let me just go a little bit deeper into this idea of the natural spectrum. Okay, so the general picture for supersymmetry is that I introduce all these extra states, these superpartners of the standard model particles, at a scale that I'll call the soft Susy breaking scale. And the experimental limit is saying this needs to be greater than about 700 GeV. And then the motivation for doing this is that I'm protected from any quadratic sensitivity to any new physics scales anywhere above the soft scale. So no matter what's happening at the ultimate UV scale of the theory, so say there's some completion of UV gravity involving many new particles at a scale, the Higgs boson, the electroweak scale is protected and can have a large hierarchy from this scale to this higher scale. However, there is some sensitivity still to higher scales in the MSSM. So there's a sensitivity to the scale at which these masses for all of these superpartners are generated. And this has a form, it's a logarithmic sensitivity to a scale we call the messenger scale. So the simplest picture for these models is that there's some hidden sector that doesn't have any standard model gauge charged particles, where supersymmetry is broken dynamically. So just like the Higgs boson spontaneously breaks electroweak symmetry, there's a sector where supersymmetry is spontaneously broken, and those effects are communicated to us through a messenger sector. And it's this scale that really tells you what relationships you should expect between the masses of the standard model particles. Of the standard model superpartners, of the MSSM superpartners. Okay. And you can see this just by looking at the one-loop formulas that you get for masses, and in particular for the relations between different particle masses. For example, if I look at the mass of the Higgs boson, it gets a correction proportional to the mass of the third generation of this Stokes square, so the scalar partner at the top, that just has a normal form of a loop factor, the coupling y top squared, which is order 1. It's quadratically sensitive to the Stokes mass, and logarithmically sensitive to this messenger scale. Right. So what you would like is that the size of this contribution is about what we measure the Higgs mass to be, so around 125 GeV. This is the idea of naturalness. And what you find is that to get that to happen, you need an order 10% to 1% cancellation, closer to 1% in most realistic models. And it's because the size of this logarithm is fairly large. So in many models of supersymmetry breaking where you have this hidden sector, the scale of this commutation of Susy breaking is around greater than 100 TeV, and in many cases as high as close to the gut scale or Planck scale. So this is what's causing the tuning problem in these models. Okay, and there's a similar problem that even if I have a factor of 10 between the soft scale and the messenger scale, I get a relationship from loop-induced couplings between the gluino and the stop that relates the stop mass to the gluino mass. Right? So this loop of a gluino and the top coupling to the stop gives me a relationship that the stop mass should be in any of these models within about a factor of 2 of the gluino mass. Okay, so what is the alternative? So what we're going to look at is models where we go away from this standard form of having a messenger sector that is independent of the other particles in our MSSM, in the supersymmetric model. So we'll look at models where the states in the theory at the TeV scale are non-minimal. So at the same time that I get the standard model superpartners, I also get the states associated with communicating Susy breaking to the MSSM. And this will allow us to get around these kind of generic arguments that there's a tuning in the standard model. And of course, this will also introduce a lot of new structure into the model. So it's interesting to see what the trade-off between introducing this new structure is and what the tuning of the model is. And of course, the other interesting thing is if this generates new signatures and new ways you might think about looking at the LHC for connections between the weak scale and other scales. So I'll talk a little bit about the new signatures associated with this kind of theory. Okay, so kind of the generic way that you can accomplish this is to extend the gaugino sector of the MSSM. So there are a few different, so the gauginos, the normal picture is that I just have a single partner, so the gluon has a single partner, spin 1/2 partner called the gluino, and it gets a Majorana mass that breaks supersymmetry. And this is what causes all the problems. But there are a number of simple alternatives where you have additional partners for the gluino beyond just a single spin 1/2 particle that fix this relationship between the top mass and the gluino mass and between the stop mass and the Higgs mass. Okay. So one of these goes by the name of supersoft Dirac gauginos, and here the basic idea is that you give the gluino a Dirac mass instead of a Majorana mass. So just the same as you can look at models of neutrino physics where you have a Majorana mass versus a Dirac mass, and they have different phenomena. In this case, you get a very important distinction that the loop contributions to the other particle masses get much softer when I give a Dirac mass to the gaugino. And this is related to the presence of some new scalar particles in these kinds of theories. Another example is models where I don't just have supersymmetry at the TeV scale, but I also have some strong dynamics associated with the gaugino sector at the scale of supersymmetry breaking. So there are a number of different ways of describing these kinds of models. So there's deconstructed models, there's Randall-Sundrum warped models, and there's models where you describe this as composite sector, like a scaled-up version of QCD. But all of these kind of have the same effect that there's these new states, new resonances associated with strong sector that also cut off this bad behavior. So the new states you're introducing are these resonances, and they are a new thing you can observe, but you're also fixing this problem with this non-minimal structure. Okay, and then the last kind of model is models where I have a flat extra dimension that's fundamentally associated with Susy breaking. And that's the kind of thing I'm going to describe in a little bit more detail. But I should say that all these models share kind of a similar phenomenology, that it's you're introducing new states at the scale of the MSM related to cutting off this logarithm, new gauge charge states, and they all kind of have similar phenomenology. So a lot of the results for this kind of simpler case, so this 5D case is a nice, easy to understand case where you can calculate everything, but a lot of the results here apply to these other kinds of models. Okay, all right, so let me then, so the rest of the talk I'm just going to focus on describing in a little bit more detail this kind of model where I've used an extra dimension to communicate Susy breaking and to solve this problem with these large logarithms. Okay, so the cartoon version of the model is that I have an extra dimension that has a size of order of the TeV scale. So an inverse TeV is a very small distance for an extra dimension. And I will have some of the particles of the standard model, so the third generation particles in particular, will live on just a single point in this extra dimension. And some of the particles, the first and second generation quarks, and the gauge bosons and Higgs bosons and their superpartners, will be allowed to propagate in this extra dimension. So this is a structure that's going to solve some of the problems in this model. And the states that propagate in this extra dimension are going to feel the supersymmetry breaking. Okay. So I'll start off talking just a little bit more detail about how this generates a natural spectrum where the top partners, so the third generation quarks are the lightest particles and have a big separation from the gluinos. Then I'll talk a little bit about how you might see these models and a little bit about how you might tell that there's some extra dimensional physics involved in these models. And this is following up, so these kinds of models have been studied by various groups throughout the years. The work that we've done on this is to follow up on some of the more phenomenological details and to study electroweak symmetry breaking and the Higgs mass a little bit more carefully in these models. Okay. So before I dive into this, so I introduced supersymmetry at the start of this, and then the other crucial ingredient in understanding these models is to understand what I mean by adding an extra dimension at the TeV scale. So let me just include a little bit of introductory material on that. So the basic idea is to imagine, let me project our three-dimensional world just down to a two-dimensional world so that you can visualize it a little bit better. So all of our three-dimensional world lives on this plane. Okay, so the question is, how do I know that there are not additional extra dimensions? Of course, if there was an infinitely large extra dimension, then I would see, so let's imagine there's some orthogonal direction to our x, y, z, our normal three dimensions. Then if there's an infinite extra dimension, I would look around and I would see 5 dimensions, right? And I would look at my Coulomb's law for charges attracting to each other, or for Kepler's law, and I would get different results because there's a very large extra dimension that I can move in. Okay, so it's obviously that we don't live in an infinitely large flat fifth dimension. Okay, so what is possible if there are extra dimensions? What could I mean by that? So what is possible is that we live in a world where there are compact extra dimensions. There are extra dimensions that don't extend for infinite length, but have some finite distance. So for example, you can imagine that there's an extra line segment at every point in 3D space that you can move along. Okay, so this has some distance, which I'll just say is from 0 to pi r. And this this can be consistent with observations if this distance is very, very small. So if the energy scales associated with probing this distance are much smaller or are much larger than any energy scales we've probed in detailed experiment, then you can have this kind of setup and be consistent with all of our observations. Okay, so the energy scales we'll be thinking about are around the TeV scale, so that the first place you would see this kind of extra dimension is at something probing the TeV scale, like the Large Hadron Collider. Okay, and if you haven't seen this before, then there's a simple way you can think about this, which is just finding out what the particles I get in this model are is just the same as looking at the classic quantum mechanics problem of finding the energy levels in of a particle in a one-dimensional box. Right? So you can think of this extra dimension as just a one-dimensional box that all of my particles live in addition to the normal 3 dimensions. And what I find is that the masses of the particles, the masses of the excitations of the particles in this direction are quantized. So for example, if I give boundary conditions that the field should be even at each brane, then I get a zero mode, which has zero energy from its motion in this extra dimension, and just has a flat profile in the extra dimension. And then I get excitations, which we call Kaluza-Klein excitations of this particle that have the same properties in 3 dimensions, but have different masses. So because they're moving, they carry momentum in this extra dimension, they acquire a mass from our point of view. So the next excitation of this particle will be at 1 over r, which you get just from solving the eigenvalue problem, right? And this state, if the radius is an inverse TeV, then this is a particle with a mass of a TeV. And you get a whole tower of these particles. You start at 1 TeV, go to 2 TeV, 3 TeV. And of course, there are more complicated setups possible, so I can choose different boundary conditions. And this was kind of the simplest possible case of taking a flat extra dimension. I could also have curvature in my extra dimensions. And this generates all types of other interesting phenomena. But here, just thinking about a flat extra dimension will be enough to capture a lot of what we're interested in these models. Okay. Good, so how are we going to use this in the context of Susy breaking? So what we're going to do is look at a model where it's the propagation of the particles through this extra dimension that breaks supersymmetry. It's not some hidden sector that has some Higgs-like dynamics that spontaneously breaks supersymmetry, but instead it's a property of this 5th dimension that supersymmetry is broken. And it is going to have some interesting features. Let me describe this in a quick way just by showing you how the I can choose boundary conditions for my particles that live in this extra dimension that break supersymmetry. Okay. So the example we'll take is just one of the standard model gauge bosons. So this could be, let's say this is the photon. Okay, then I know that the photon is massless, so I would like to choose boundary conditions for the photon for this gauge field so that I have a massless photon. So that just means that it has even boundary conditions at at this w equals 0 and w equals pi r, and then I'll get this flat mode that is massless. So this is how you get a massless photon out of an extra dimensional theory. And then there will be a whole kk tower of excitations with masses starting at around around a TeV of excitations of the photon. Then I would also like to have a superpartner of the photon, so a gaugino partner of the photon, but I would like it not to be massless because I want supersymmetry to be broken. So I can choose boundary conditions so that it's has its mass lifted from 0, so that it's even here but vanishing here, so its first state is at 1 over 2r. And in 5D, I have additional superpartners, and I can do a similar trick so that all of their masses are lifted. Okay. And so this clearly breaks supersymmetry, and I will explain in a few slides why this is a nice way to break supersymmetry. Okay, and the way we'll put the particles of this MSSM into this model is that all of the standard model particles, which we would like to have to leading order a 0 mode, so a massless mode, will have these boundary conditions that give you a 0 mode. Then there are all the MSSM partners will get profiles that look like this and will appear at 1 over 2r. And all of the extra superpartners that we're adding in our model, so this is the extra structure in the model, is these extra superpartners, will also have boundary conditions that give them masses at 1 over 2r and 1 over r. so around the TeV scale. And then the third generation, so the top quark, the bottom quark, and the tau leptons, we'll put on the localized on one of the branes, localized at a single point in this extra dimension. This means they don't propagate in the extra dimensions, and so they don't feel the Susy breaking associated with extra dimensions. So these start with masses at a tree level, they don't know anything about Susy breaking. So it will only be through the couplings to the particles that do propagate in this extra dimension that they feel Susy breaking. Okay, so the practical thing is, what is the spectrum I get out of this, because this is what's going to matter for looking for these theories. And so what I get at tree level, so just with the boundary conditions I've described, I get a set of particles, this spirimions, the gauginos, and the Higgsino, the partner of the Higgs, are all degenerate with each other at a mass of 1/2R. And the third generation squarks, and the Higgs boson has a mass of 0. Okay? Right, and there's two different mechanisms protecting these things. So because the third generation is localized on the brane, so it doesn't propagate in the Susy breaking dimension, that's why it gets a mass, that's what protects its mass at tree level. And the Higgs is protected because I've chosen boundary conditions that give it a 0 mode. So there are some interesting features of this model compared to the MSSM. So an important thing in the MSSM is that to give the Higgsino, the partner of the Higgs, a mass in the MSSM, I have to give a mass to the Higgs boson of the same size. So a 300 GeV Higgs boson, or a 2 TeV Higgs boson, means I have, so say I have a 2 TeV Higgsino, then that means there's a contribution to the mass of the Higgs boson of size 2 TeV. So to make that, cancel that off and make it small, I introduce a lot of tuning. I have a lot of problems with naturalness of that theory. This model has, because of this special structure of this model, I can get a Higgsino mass that is at 1/2R without introducing any tuning. So that could be at 2 TeV without introducing any tuning in the Higgs mass. So this is a very special feature of these models that's quite appealing. The other interesting thing that's different from the normal MSSM is that in the normal MSSM, all the gauginos get a Majorana mass, and in these models you'll get a Dirac mass. So you have extra partners for the gauginos, and you get a Dirac mass with those states instead of a Majorana mass. And this helps with, so in Susy models you sometimes have flavor problems, so the propagation of these extra superpartners can cause problems with rare flavor observables, and the fact that you have Dirac masses for these states suppresses lots of these observables so that they're not a problem in these models. Good. Okay, so kind of the crucial point for why, so this, it seems like we've introduced a lot of structure in these models. So there's one nice thing about breaking supersymmetry in this way that's very important, which is that the scale of Susy breaking, so this messenger scale where Susy breaking is communicated to our particles, and the scale that cuts off these logarithms and tells us how the different masses in the spectrum are related to each other, is generated at the same scale as the mass of the particles. So it's all generated at once. And the way this works is that although I've chosen boundary conditions for my particles that break supersymmetry, so that the 0 modes, I have a splitting between, I have a massless gauge boson, but I don't have any massless gauginos. I've done this in a way that locally in this fifth dimension, so that any point in this fifth dimension, there is a Susy that is preserved. So there's a good symmetry locally, and it's only broken when I look at effects that happen over here and simultaneously, so at both sides of this extra dimension simultaneously. So there's a locality in the Susy breaking that protects you. So kind of the cartoon version of how this works is that I set in supersymmetry, I have a gauge boson that's related to a spin 1/2 particle, and has the same properties as that. So if I choose boundary conditions so that this gauge boson and this gaugino have the same boundary conditions here at this y equals 0, that is w equals 0, there's no difference between them locally here. So here I can define a supersymmetry transformation that is an exact symmetry of the theory locally, because there's nothing distinguishing these two states here. And likewise, I can pair this spin 1/2 particle with this spin 0 particle and define a supersymmetry transformation that relates them, and there's no difference between them here, because locally they just have this matching boundary condition. Whereas on the other side of the interval, I can define a supersymmetry transformation that links this spin 1 particle with this spin 1/2 particle. So here I have a different supersymmetry, but it's still protecting me locally. And likewise, these two are paired together and locally protected. So what that means, and this is a trick that we use quite a bit. So this trick is good in the context of supersymmetry. This is also kind of a more general thing that you can imagine doing in many models of coming up with how do you protect some symmetry approximately in a model. So this is useful in constructing inflationary models or constructing models of axions as well. And the point is that when I need to feel an effect on both sides of an extra dimension, if I look at virtual particles, as I go to high virtual masses or high virtual momenta, the propagation of this particle across this extra dimension is exponentially suppressed. So if I look at virtual momenta much larger than the radius of the inverse radius of this extra dimension, so in this case, virtual momenta much larger than a TeV scale, these loops become exponentially suppressed, which is a much more rapid suppression than the normal power law suppression that you get for loop diagrams. So this is kind of the fundamental thing that is protecting this symmetry. And it's a trick that you can use for a lot of things in lots of cases where we'd like to protect symmetries to describe various phenomena. Okay. And the effect of this is that we just get a messenger scale that's around a TeV. So it's what I claimed would be a good thing for us. Okay, so to put in some numbers, so we started with a model where at tree level the Higgs boson was massless. At loop level it couples to these states that feel the Susy breaking boundary conditions. But it couples to them very loopy, and these loops are cut off at the TeV scale. So I find that I get a very large natural hierarchy between the Higgs boson mass and the mass of the particles in the loop. So in particular, coupling the Higgs boson couples to the Wino and Bino, the partners of the electroweak gauge bosons, that propagate the bulk, and that gives us a mass of about 1/30th of the weak scale. 1/30th of the scale 1 over r. So that means that if the Higgs boson is at the mass of the weak scale, then there's a natural hierarchy of a factor of 30 between the Higgs boson and this scale of this exponential 1 over r. So that means the natural scale for these extra dimensions is around 4 TeV. So this is very interesting. The starting point we had is that in these general models, there's no hierarchy between the scale of Susy breaking, the scale of the superpartners, and the scale of the Higgs boson. But here is a model where there's naturally a factor of 30, which is observationally very interesting because this is right about where the limits on superpartners die out, is masses of a few TeV. Okay, and likewise, not only are we able to separate the Higgs from the superpartners, but we're also able to separate the stop squark from the gluino, which is observationally an interesting statement because the limits on the gluino are much more robust and much harder to avoid than the limits in the stop. So if you want to play any of these games that people have come up with to hide the superpartners by giving them different decays, then this works best in models where I have the gluino much heavier than the stop squark. And here I naturally get a factor of 5 between these masses, where this is very difficult to get more than a factor of 2 in a typical supersymmetric model. So these are the two big things I've won by putting in this extra-dimensional Susy breaking. Okay. So the other nice feature of these models is that I've put in just a single scale in these models. So far the only parameter that I've added to this model beyond the MSSM is the size of this extra dimension. And everything else so far has come just out of this parameter. Okay. So even though I've added all these new particles, it's this one parameter, the size of the extra dimension, that's setting all of their mass scales and setting all the extra properties of these particles beyond the central. So you can ask an interesting question, is in that single parameter model, does electroweak symmetry breaking work? And the answer is, unfortunately, no. In that simple model, you don't get electroweak symmetry breaking. So although we get this nice natural hierarchy between the mass of the Higgs boson and the mass of the superpartners, we get a contribution to the Higgs boson mass that's positive, so it doesn't drive electroweak symmetry. You need a negative mass in the Lagrangian for the Higgs boson to get a electroweak symmetry breaking potential. Okay, so fortunately there are some extra contributions to the massive particles. So what I've talked about so far are kind of the leading contributions. There's some extra contributions that have to do with the fact that anytime you have an extra dimensional model, if I want to put gravity into this model, then that extra dimension becomes a dynamical object. So the size of that extra dimension is related to a mode that's the fluctuation of the graviton in that extra dimension, right? So we call this the radion. And this has some important effects, and particularly you have to put in some dynamics. If you want to say that there's a compact extra dimension, then there should be some dynamical potential that stabilizes that radius. So we want this radius to be at a TeV. So there's some extra physics related to the TeV scale that stabilizes this extra dimension. I won't go into the details, but you get a typical size. So this involves some extra Susy breaking, and kind of tells you what your uncertainty. So I said there's this loop level contribution that gives me a pretty concrete prediction for what the masses of particles will be, and then there will be extra contributions from this effect, which you have less control over. And these, it turns out, give you an uncertainty that's kind of comparable to the loop prediction. And what that means practically is that all of the states that propagated in the extra dimension and at tree level got a mass of around 1/2R, so a mass of around the TeV scale. That is the dominant effect for those states, and so you know that those masses are all around a couple TeV. However, the states that were protected at tree level and only got a mass at loop level, they get a mass from loop level contributions from these states, but they also get a mass that is not predictive from this extra effect. So you know the overall mass scale of these states is a factor of 5 or 10 below the heavy states at 2 TeV, but you don't know what the actual values of these masses are. So if you're thinking about the phenomenology of these models, and if you're thinking about electroweak symmetry breaking, it's possible that there's kind of any ordering for these masses. So what you've predicted in this model is the overall hierarchy, but not the relative masses of these states. So you could try to develop a full model where you have predictions for all these. So this would be, you write down some string theory that gives you this particular field theory model out of it, and then you know all the targets. No one knows how to do this yet, but from a phenomenological level, we can just parameterize this. So this is our definition of our model, is that I have some states at 2 TeV, this set of states at a factor of 10 below, and I can just study what happens in these models as I just choose different parameters for the relative size of the masses of these third generation particles. Okay, so this will let me get electroweak symmetry breaking, and will also give you a lot of possibilities for what the phenomenology of discovering these models might be. So the other question is that, do I get, okay, we can get electroweak symmetry breaking to happen with the right VEV for the Higgs boson. The other question is, in that vacuum, do I have the right mass for fluctuation of the Higgs boson? So do I get the right Higgs pole mass of 125 GeV? And as I mentioned earlier, this can be difficult to do in supersymmetry. So you can get this just in this model I described by putting the stop quarks at around 3 TeV, then they radially generate a contribution to the mass that's large enough. But this will lead to models that, although less tuned than MSSM, still are tuned at the 1% level, by which I mean they have their actual mass of the Higgs boson is around 1% of what you would have expected from the natural value. So there are a few different options for how you can fix this, and all of them basically involve adding extra states into this bulk that couple to the Higgs boson. So a nice thing about these models is you already have some dynamics at a TeV scale. So adding these states is, there's a nice way to get the extra scale you need to add these states in this model, but I'm not going to go into the details of that. Okay, so the overall interesting plot you can make is as a function of the mass, the size of 1 over r of this extra dimension, so the mass scale of these extra states, what is the tuning of these models, and compare it to experimental limits. And then this vertical axis will be, in the particular model I've chosen, there's an extra gauge boson that there are limits on as well. But that won't be important. Kind of the numerical result is that at the current LHC limits, in this kind of model where I've added all this extended structure, I am not really tuned. So my tuning is a factor of 2, whereas in these more traditional models where I don't have this low scale of communication of Susy breaking, I'm tuned at the level of 1% or worse usually. So I've gained quite a big factor. I've gained a factor of 10 or 20 in tuning, but I've also added a lot of structure. So let me briefly talk about what you might expect the phenomenology of these models to be. So like I said, a prediction of these models is a big hierarchy between the gauginos, Higgs-inos, and the third generation squarks. So this model is a model where the first things that I would expect to produce and see at a hadron collider, like the LHC, are producing these third generation squarks. And then they can decay to all the lighter states. And there's, in detail, what you look for depends on, so it depends on the ordering of the spectrum, because it depends what things this particle can decay to. And in particular, this model also has some interesting possibilities for what the lightest particle is that are a little bit different from the MSSM. Good, so let me just talk about the simplest version of this, where the superpartner of the neutrino is the lightest supersymmetric particle. Okay, then something interesting happens. So there are other ways of getting the spectrum than the one I've described, where the third generation is the lightest particle. So this is called a natural Susy spectrum. But the generic thing you expect in most models, where you have a natural Susy spectrum, is that the Higgs-ino, the superpartner of the Higgs, is one of the lightest particles in the spectrum. Okay, and then when you produce these third generation squarks, they always decay through this Higgs-ino, or very often decay through this Higgs-ino. This gives you a quite distinct signature that is not present in these models, because these models have the somewhat unique feature that the Higgs-inos are very heavy. And so what you get instead in these models are decays that go off shell and go through a 3-body decay instead of a 2-body decay. So you can decay through a very heavy LINO, so it doesn't get produced on shell, but through the off-shell interactions can decay to, for example, a neutrino and this neutrino. And you get different kinematics for these decays and different final states that might be interesting to look for. So just for example, in this, if I have production of a right-handed top squark or a left-handed top squark, then I'll get states that have these 3-body decays and are very rich in V's and tau's, so giving me different final states and different kinematics. And so you can't actually directly take this 700 GeV limit on these models. So it's an interesting direction goes to figure out how to, if there are better handles for looking at these kinds of decays of supersymmetric particles. Okay, and then there are a few other possibilities for what the LSP in these models is. These also can generate phenomenology that's different from your normal expectation from the MSSM. So I think it's interesting to look at how these are covered by clouders. That's something we're working on right now. But let me skip over that. Okay, and I'll just say one thing about the question of, so the first thing that you would expect to see in these models is these third generation particles, but then it's fair to ask the question, how would I know that this is the mechanism of Susy breaking? So how do I know it's this mechanism instead of some other mechanism that also gives me this kind of spectrum. So in that case, what you would like to see is some physics associated with the fact that there's an extra dimension in these models. Okay? And a feature of these models is that this is difficult to do. There's something called KK parity in these models, which is that, so what I would like to see is I have these zero modes of my standard model particles that are the things we're made of, but you would like to be able to produce, when I collide particles together, for example, the first KK mode, so the first excitation of the Z boson, for instance. But what happens in these models is that there is because these models don't distinguish, at leading order these models don't distinguish the y equals 0, or this side of the model, sorry, this side of the extra dimension from this side of the extra dimension. There's a parity that I can do, so I can just flip the directions of the extra dimensions, right? And that is a good symmetry of the model at leading order. And so that is a parity under which these first KK gauge bosons have opposite signs. So the model is symmetric under that, but this first excitation flips sign under this. So it has parity -1 under this, whereas my standard model particles have parity 1. So this is a conserved quantum number that forbids processes where two standard model particles produce a single KK excitation in a collision. So I have to pair produce these states, or I can produce higher KK excitations that have KK parity of 1. Okay, so this is not particular to this supersymmetric model. You can also write down just normal models that don't have supersymmetry but have extra dimensions, and this is a property that these models can have as well. So this phenomenology has been studied quite a bit. But okay, so the interesting point for this model is that you might have expected to actually see the leading signatures of these models be these KK gauge bosons, but because KK parity forbids the single production of the lightest modes, you would expect to see first the superpartners, and then later at higher energies you would see the production of these 5D states. But that would be the next thing to look for. Okay. So in these models, there is some difference between this side and this side, because I've chosen to put some of the matter on one of the branes. So there is a small breaking of KK parity from this choice. And so something that you might see, and that might tell you about the structure of the model of having some states localized, is that this KK parity would be an approximate symmetry. So you would have a suppressed amplitude to singly produce these KK excitations, these exponential copies of the standard model particles. And the decays would be preferentially into the third generation particles, because those are what are breaking this symmetry. So I might expect to see production of this extra resonance that then decays to two top quarks, for instance. Okay, and there are variations of this model, however. So I focus on a model where some of the standard model is on the brane, so some of the matter is on the brane, and some of it's in the bulk. There's some interesting variations where I put all of the matter, so all of the quarks and leptons on one of the branes. And then in these models, they have some interesting similar properties, but the leading signature of these models is actually the production of the KK states instead of the production of superpartners. And I can do fun things like put in extra dimensions and put some of the gauge symmetry in one direction and some of it in others. So there's kind of a rich set of things you can do. So what I described to you was kind of the simplest model that has this nice feature about extra-dimensional Susy breaking, but there are a lot of variations that can change the phenomenology, and that's interesting. Okay. All right, so let me conclude then. So kind of the fundamental picture is that the reason to look at this five-dimensional Susy breaking is that by associating Susy breaking with this extra dimension, I all at once have this idea of locality being able to set up this natural spectrum at tree level, and then protect it from loop corrections. Whereas in normal high-scale Susy breaking models, I always get these relationships that are basically irreducible between the masses of my superpartners and the mass of the Higgs boson that give me a problem with tuning, with the idea of naturalness. And I can embed this in a model that accommodates the 125 GeV Higgs. From the point of view of phenomenology, there are some interesting differences between this way of generating a natural Susy spectrum and some more traditional ways. and particularly these heavy Higgs zeros kind of change the signatures of the third generation states. And if I want to probe these models further, if I was so lucky as to discover some superpartners at the LHC and was wondering if this is what's going on, then the next thing you might look for is these resonances, these KK excitations of the standard model particles. Okay, so when giving a talk like this, it's a little bit hard not to sound like a hopeless optimist. So let me temper my conclusions a little bit. So I kind of view this as an exploration, is an exploration of how you make trade-offs between increasing the complexity of the model, so going away from the minimal extension of the standard model, and this concept of naturalness, right? So I would say if you see Susy, I guess kind of if you see Susy at low energies, what the current LHC results are maybe suggesting is that it might be associated with more than just a minimal structure of the model. It might be associated with some new dynamics associated with communicating Susy breaking nearer than you might have expected in a high-scale model. So the other thing is that in this kind of regime we're in parameter space, in these kinds of models that you still have naturalness and Susy, because of the extended structure, other properties of the model, so for example, these gauge excitations and KK excitations of the standard model particles in the dimensions, might be the leading signatures of these models. So in this sense of supersymmetric naturalness, naturalness and Susy right now is kind of favoring extra structure, and you might see this extra structure first before you see supersymmetry. So it's an interesting thing to keep in mind. So if you see something unpredicted at the LHC, it's not guaranteed to have anything to do with supersymmetry or naturalness, but it might, and there's interesting ways to test that. Okay, and then the other question is, if I see nothing at LHC 8 and I don't see anything at LHC 14, can I still learn something about naturalness at the LHC? At future proton colliders, for instance? So for instance, a 100 TeV collider. And I'd say this is kind of a example that you can use as a benchmark, right? So this is telling you, after the LHC 14, this model is still in a part of parameter space that's fairly natural, even if limits on superpartners increase by a factor of 2. So this is, you can make your own judgments about the aesthetic value of this model, but it's kind of a benchmark or a proof of principle of what it takes to have naturalness after LHC 14, and if you think that is a good thing to keep looking for at future colliders. So you still might learn something interesting even at higher energies about naturalness. Okay. So thank you very much for your attention. Yeah.
Any question?
Yeah.
I heard about some rumors that in LHC they found an XX in the diphotons channel.
At 750 GeV.
Yeah. What do you think about that? Is that related to your models? Or?
So I've thought a little bit about this. I have not thought exhaustively about possibilities of doing this in supersymmetric models. I don't think it's simple to explain this in a Susy model. I think composite Higgs models, I personally think have a little bit better chance of explaining this. So if this is real, if there's really a diphoton nexus at 750 GeV that we didn't see at the 8 TeV LHC, but we've seen at the 14 TeV LHC, then that is a fairly restrictive set of observations to fit. So you kind of need a state that has a high branching fraction to diphoton to see it first in that channel. Not super high. It can be dominated by other things, but you need kind of diphoton to be with greater than 1 in 100 branching ratio, which when you get to a state that's around 750 GeV, if it mixes with the Higgs boson at all and has couplings that looks like the Higgs boson, then that kind of state at 750 GeV will like to decay to gauge bosons and to top quarks because there's no kinematic suppression to go to those states. Whereas the diphoton process, if its couplings are Higgs-like, then it has to go through loops. So it's not clear how to get a good state to do this in Susy to me. But in composite Higgs models, I think there might be good ways to do this. So if you have extra pseudo-Goldstone bosons, that might couple to diphotons is one example. I mean, the other challenging thing with this rumor is that if you imagine just producing this state singly, so I just produce, I have through gluon fusion, so you can imagine the exact same thing, the Higgs I mostly produce through gluon fusion. If I produce this new state mostly through gluon fusion, then the cross sections don't really work out right, that I should have seen it I should have really seen it at 8 TeV if I was seeing it now at 14 TeV. So you kind of need to think about what is a good production mechanism for this. So something like pair production might scale more favorably for this kind of state as well. But yeah, I'm excited. The announcement is at 1 a.m. tonight, so we'll know more soon, I guess.
You put the first and second generation formulas in the bark, and the third generation formula in the brain.
Yep.
Why do you make this difference?
So this is, so good question. So this does two things. So one, because of this issue of KK parity, if I put the first two generations on the brain, then my leading signatures are through producing these KK states, because then I don't have any protection from KK parity, so I can produce the KK Gooch bosons. This is still an interesting model. It has a lot of good properties still, but it's a little bit, the limits on those states make it a little bit more tuned than the model where only the third generation is on the brain. But I think those are also interesting models to think about. And in fact, putting the third generation on the brain and the first two models in the bulk, although it's good from the sense of tuning of the spectrum, it does make, it kind of puts you on the edge of some flavor observables, because the localizer third generation introduces a new flavor direction. So there's some third generation flavor processes that are, you become sensitive to these models in the case where you have the different localization for the first and second generation and third generation.
And the standard model particles are the zero modes in your models, right?
Yeah.
So how do you determine the 1/R in your model?
So how do you stabilize the 1/R? Yeah, so you would like to, there's a one irreducible contribution to the potential for the radion is the Casimir energy of these states. So there's been a number of groups have studied how you can stabilize this. So you need a little hierarchy between whatever this gravitational scale in the fifth dimension is and this scale of a TeV. So you can get that to come out of just the Casimir energy balancing for different states. So the Casimir energy from the bulk states can stabilize the radion.
Any more questions? Okay, if no more questions, let's thank speaker again.
Thank you.